Well, in this video, this is the third in a sequence of videos on C++ C++ models. In this video, we will be discussing memory model and C++ classes. So the C++ memory model divides memory into static memory, stacked memory, and heap memory. Variables stored in static memory have the lifetime of the program. Stacked memory is allocated anytime the thread of execution enters a scope. You call a function, you enter a for loop with curly braces. Anytime you enter a region defined with curly braces, stacked memory is allocated, and the lifetime of that allocation exists from the time you enter the scope until you leave, the thread of execution leaves that scope. Finally, heap memory is native heap in C++, and that heap allocation starts when you make a call to new and ends when you make a call to delete on a variable that's stored. So how do you place variables in these various memory locations? For static memory, you simply declare the data item. You qualify the declaration with the keyword static. That places a variable in static memory, now has a lifetime of the program. To declare a variable in stacked memory, anytime you're in a scope, function scope, perhaps, you simply declare the variable that places it in the stack frame, the stack memory allocated to that particular scope, and the lifetime for that variable lasts from the time you declared it until you reach the end of the scope. The thread of execution exits the scope. Finally, you place a variable in heap memory by calling new, specifying the type you want to create, and you may initialize it to give it a value. This is an unnamed type, but you have a pointer that called the new returns a pointer to that memory, and that variable lives until the program calls delete on that pointer, and that removes the allocation. Okay, so let's now turn to classes, C++ classes. A class typically manages data. I like to think of a class as a unit of data management. Each class has a body of code in static memory, and that code has a series of functions which access instances of data wherever they're stored. I'm showing you in this diagram on the stack memory. That's typical. You know, when the class basically acts like a cookie cutter. When I declare a variable of that type, it just stamps out a region in memory with the data members for that type. And, you know, if I declare it again, it stamps out another variable. And it initializes always. The language guarantees that these allocations will be initialized so they're valid objects. Next question is, when we call a function, for example, this is a point class and it has a name method. And so if we call p1.name with some string, in this case p1, that's mutating the state. And the question is, how does this code find the object to mutate? And the answer is that every call from a non-static member function passes its address to the code, to the class code, identified by this identifier, THIS, this identifier. And so this, when we call p1.name, that sends p1's address, and then the class code simply changes the name in this class to whatever we supplied, in this case p1. Okay, so you know, and that same thing happens with P2 and P3. So the code only has a single slot for this pointer. So it's not really holding all three of these pointers at once. It only has a single slot. But every time we call a function, that slot is filled by the address of the object that invoked the function, in this case, P1, invoking name. All right. So here's an example, a point class. So it's class is designed to model points in some space. So if this happened to be space-time, we'd have a height, width, and depth variables and a time variable. So our coordinates would hold height, width, depth, and time. But we might perhaps be implementing designing a air quality monitor, and air quality we might want to measure temperature, humidity, carbon dioxide, carbon monoxide, volatile organic compounds. You know, there might be 10 or 15 variables. In that case, there would be 10 or 15 coordinates in a space. When we declare a point locally in some function, the member data of that class is going to be stored in stacked memory, just as we described in the previous memory model. So here, in this case, when we declare point, we're storing a string name and a vector of doubles. A vector is just like an expandable array on the stack, but that's not the whole story. The string class itself stores the character sequence for name on the native heap. And the vector stores its collection of data in a contiguous hunk of memory on the native heap. And you know, we don't have to worry about that. The string manages its allocation, vector manages its allocation, but these two guys, their storage occurs in two places. The control data is on the stack, here and here and here, and the user data, the characters for name and the values of double for the coordinate values, they reside on the native heap. And again, you know, our program doesn't have to manage that. That's all managed by the string and vector classes, instances of those classes. So when we measure the size of that object, there's a size of operator. When we measure the size of this point object, we'll measure the size of name and vector, but all we're measuring is their size on the static, you know, in their static allocation. We're not measuring what they hold on the heap. So for example, a string with 50 characters has the same size as a string with 300 characters because we're not measuring that character space on the native heap. You know, the reason it works that way is that the compiler needs that static, the size of that static control stuff for string and for vector in order to lay out the code. When it's laying out the code up here in, for the point class, it needs to know that static allocation. But the dynamic allocations, the character space for the name and the coordinate space for the vector, they're defined at runtime. The compiler has nothing to do with that. And so size of measures what the compiler needs to lay out its code. Okay, now let's talk a little bit. You know, you don't need to worry terribly about all these details, but let's do a quick walkthrough with some of these. You'll notice here's a function point, same name as the class. Any function with the same name of the class is a constructor. That's what's used to initialize each one of these instances when we create them. This constructor has a size n, which describes the number of coordinates, and a name, which defaults to none, meaning we haven't defined a name yet. There's another interesting constructor, point, that takes a standard initializer list. This is a initializer list is a container from the standard library, And when we build a constructor that accepts an initializer list, that allows us to initialize it with a braced set of values. So in this case, we'd have a braced set of coordinates: height, width, depth, and time, perhaps. Okay. So, and then we have a name function that mutates the state. And we have an overload of that name function that takes nothing but returns the string name, and it's declared to be constant. It's qualified by this const, and that means that we can call this name on a constant point. We can't call this name on a constant point because this will mutate, and we're not allowed to do that with a constant object. We have a couple of index operators that allow us to index down through this vector of coordinates, to pick a particular coordinate we want. This one returns a reference to a double, meaning that we can modify that. We can read it, but we can also write to that particular coordinate. So if we have operator 2, we have the potential of writing to the third coordinate. They starting count from 0, 0, 1, 2. So the third coordinate. But there's another index operator that returns not a reference, but a value, a double by value, and is qualified as const. And the reason for that is that if I have a const point, the compiler won't allow me to call this operator, this index operator that returns a reference, because that can mutate the state. Won't let me do that on a constant object. If that's the only index operator I have, I can't index that constant object. Even if I only want to read it, the compiler isn't going to do that analysis. It just says, hey, I've only got an operator that can mutate. But if we provide this this operator for const, then indexing of that constant object will succeed, and the compiler would just use this const version, and so on. We have iterators that allow us, there acts something like pointers that allow us to index through the vector. And if you read through the C++ story from which these models were drawn, you'll see that you'll see lots of uses and explanations of the iterators. So that's an example of point class, example of a class called point. Okay, so we're going to stop here. The next video, the part 4 of this video sequence, we'll talk about object models. And this is probably the most important of the models. You don't really understand how the language works and can't use it as effectively as you should unless you understand this object model, and we're going to do that next. So for now, we'll say goodbye, and thank you for your time listening to this video, and I hope you'll join us for the next one.